All right, so today we're going to be talking about big O notation. Can someone tell me what they think big O notation is or does?
Denotes the upper bound of the runtime of an algorithm.
Okay, and it does, yes. So big O notation is used to describe the relative performance of an algorithm. And this is not necessarily how much time the algorithm takes specifically, but how is it affected by change in input size. So if you have a function that takes in input, let's say it takes in an array as input, how will this function, how will it be affected by having 10 elements in this array versus a million? So this is what we are trying to capture with big O notation. So big O is the complexity of the function. So that's the O in terms of the input size, N. So we're generally concerned with how much, we are generally concerned with how much an algorithm takes to run based on the input size, as well as how much memory it would take to utilize this. So the big O, there are two types. There's a time complexity and there's a space complexity. What does time complexity mean?
How long
Is
it
it-
takes to run?
Yeah, how much time it takes for an algorithm to run or program. Space complexity?
How much memory is used?
Memory.
Yeah, exactly. How much memory is using, how much working space is required to run the algorithm. So it's not how much space you're using to like if you're saving files or something like that. I'm not talking about that. I'm talking about inside your program when you're running, how many like objects are you creating? How much memory are you using while you're working? Yeah, like the RAM that we were talking about the other day. So that is working memory. Okay, so let's look at this code here. How long would this first loop take? Oops, that was not what I wanted to show. So this loop goes from 0 to 5 or 0 to 4. And for every iteration, it prints out hello there. So how many operations is this?
5.
5. So this is O of 5. What about this one? So we have an array. Let's say this array is of size n. So we're looping through the array. How much would this take?
O of n.
O of n. And then the next one, this should also be the same, right? O of n. And then these three down here.
O of 1.
Yeah. So for our sake here, we'll just say O of 3. But generally, when we are referring to constants, so anything that's a number, we just say O of 1. So this is O of 1, this is O of 1. But to calculate how much this algorithm, or what's the complexity of this algorithm, we pretty much add all of these terms. We add like terms, so this is O of 8 plus O of 2n, and then we get rid of all the constants. We don't care about the constants. And then we're left with O of n. So the complexity of this entire algorithm is going to be O of n. So generally, when we're looking at an algorithm to determine what the complexity, the time complexity is, we take the largest term. What is the thing that is taking up most of the time. Okay, so these are some of the most common ones that we see. So we have constant, logarithmic, so log n, O of n is linear, and log n, and so on. So these are in order from best case to worst case. So if our array is size 10, and if we have a constant algorithm, that means that, actually, let's go back here. So if our array size here grows, what will be affected over here? So which loops, which pieces of data would be affected?
The O of n's.
Yes, exactly. So our constant ones pretty much happen instantaneously. It's not actually instantaneously, it's taking like a very small amount of time. But for our purposes, when we're trying to capture what the overall complexity is, we say that, so if this array was 1 billion items, this will still print 5 times. Nothing will happen differently. So here, when it's constant, n equals 10, it's just gonna still be 1, right? It's gonna be, it's generally gonna print out 1-ish times, or it'll take 1 unit of time. With log, it's still pretty small, linear. So with a size that's 10, it's gonna be 10 because linear goes straight up. So it'll take 10 times the amount of time versus if it was just a 1. Log linear and log n is also not too bad here, you see. But then when we get to quadratic, it becomes double, like 10 times the amount. This is 100 times the amount of, or the size of the array. And then exponential, right here, it's not too bad. Factorial is getting up there. So if we just increase by 10, so our size of the array, the size of our array is 20 now. We see here, log didn't change too much. Linear increased with the same amount or the same rate as this increase. Quadratic is now further, and then cubic is even further now. Exponential, it's already 1 million for a size of 20, don't forget. And factorial is just a very large number. And then, oops. And then same here, log stays relatively small, linear, like we said, grows linearly, and they keep getting worse and worse. So we see that the exponential and factorial are pretty bad. Does anyone know what log is? Oh, actually, Sid, you have your hand up.
Yeah, Zainab, can you just go over why something like 2 of n or even 10 of n reduces to just n?
Yeah.
Or I'm sorry, 2 times n or 10n.
Yeah, 2 times n, it's because relative to having like an n squared, a constant times n is not n squared. So I don't know the meaning behind, or not the meaning, sorry, the reason behind the choice of doing that, but what I remember is because it's negligible in a way. So saying 2n versus 3n, it's not that big of a difference when you're comparing array sizes.
Yeah, exactly. Like what we're interested in is like if the input size, like for example, we're sorting an array or going through an array. If I have an input size of 10 things, how long does my program take? If I have an input size of like 1,000,000 things, how long does my program take? If I have an input size of 10,000, 100,000, 100 million. So like, we don't care about the difference between 1 million and 2 million, between 1n and 2n. Like, we care about the order, like the difference between like 100, 1,000, 10,000, 100,000, 1,000,000, because once we start getting up there with big numbers, when program efficiency actually matters, like the difference between 2 million or 3 million is trivial, essentially. So it's like a very broad brush that Big O is painting with. Like, it's sort of like a tool to help us get a big picture sense of things.
Okay,
Yeah.
thank you.
Thank you, Adam.
Yeah, for sure. No, I know it's been a minute since I've done this as well. We did a lot of this in school, and it is really good to know, because it gives one of our other teachers, Benjamin, we were chatting about this in Slack. He made a really good point that even though we don't use this stuff, kind of knowing these concepts gives you the tools to talk about and describe and like think about problems. And Big O is a great example of that, because you probably won't use it, but you do, both in technical interviews and on the job, want to be cognizant of like, how much data am I dealing with? Because you have to think differently about sorting through a list of 1,000,000 things versus 100 things.
Yeah. Thank you, Adam. Oops. So, does anyone not know what log is? You can raise your hand or put in the chat. Yeah. Who would like to explain log?
I always need to like reread what log is, because it is a kind of tricky to explain. So that
Yeah.
would, thank you in advance.
Sid, you wanna take a shot at it? Or was that from before?
Is log kind of like base?
Oh, that was from before.
or like, like base 60 or whatever, like type math.
It's the exponential function.
Instead of, so if you want to square a number, you can go, you can raise something to a half power. So 25 raised to the half power is 5. And that's, in my mind,
But that's, no, a logarithm is an inverse of that. It's the inverse.
well, the inverse of 2 is 1/2.
Take it, Spence.
So here, it is, there's an equation, hold on. Oops.
Yeah, I'm looking for a good graph as well. I can also take a crack at this if that'll be useful.
Okay. So we're just gonna look up the formal definition. What is log? Because I would not be able to do it justice if I just kind of said what's in my head.
Yeah, I'd be in the same book, to be honest.
So log is the inverse function to exponentiation. So pretty much you have a number that, let me show you an example here. That's a bad example. Okay, this one. Did not want to, okay. So if we said 2 to the 4, right, 2 to the 4 equals 16, log of 16 equals 4, or log base 2 of 16 equals 4. So you're pretty much finding what is the exponent that I would have to add on to the base to get this number. and that is your result. So with computers, we're usually always using base 2 because of the binary system. So if you have, let's say you have an array or a tree that has 16 elements. If the traversal program takes log n time, that means if it's 16 elements, it will take 4 runs to actually get to the answer. So binary search, you guys have heard of binary search, and that is a log n algorithm. So that means for whatever the size of the array is, the actual amount of operations that you will have to take will be a log of that. So if we have a size 16 array, to actually get to the right answer, worst case scenario is it's going to take 4 operations to do it. And we'll see, there's a little animation of that to see later. But does that kind of make sense about log? Yeah, no. It's
And just to,
yeah.
no, it is a tricky one. I'm going to throw in, I'm borrowing from Wikipedia. I always will pick like 100 as my example when I have to remind myself of how log works.
Mhm.
Like if 10 squared is 100, then log base 10 of 100 is 2. And then in the Wikipedia example, like if 10 cubed is 1000, then log base 10 of 1000 is 3. So it's not as accurate as the definition that you were sharing, which is definitely more precise and like describes itself what it is. But that's the example I'll go to remind myself, like, all right, I know that if I raise a number to a power like 10 to the second, 10 to the third, I get this big number. But if I want to go backwards, and if I have like 10,000 and I want to know what power do I have to raise 10 to, like how many times do I have to multiply 10 by itself to get to 10,000, that's the logarithm. So I have to multiply 10 by itself 4 times, 10 to the 4th, I think, to get to 10,000. So the log base 10 of 10,000 is 4. And actually, I'm going to very quickly steal. I wanted to steal Wikipedia's graph. I'll just quickly steal and share this image. We probably have this. Can I share my screen for 1 sec, Sana? Thank you. And again, I apologize that this image is super rough, but the key thing here is that, like, unfortunately, the numbers on this scale are too low to make this really interesting, but like something exponential grows really fast. Like, 2 to the 3rd, 2 to the 4th, 2 to the 5th, 2 to the 6th. I think it's like, 8, 16, 32, 64, 128, 256, 5, 12. We're raising the powers of 10. It's like 10, 1,000, 10,000, like exponential. Anything exponential grows extremely rapidly. The log, because Zainab, exactly like you were saying, it's the inverse. We're looking, it grows much slower. And that's the only thing I wanted to share. And that's, like, for our purposes, for analysis of algorithms, that's one of the critical pieces. And I should just pause there too, because I will probably start putting my foot in my mouth if I start trying to talk about it more, because it is a little tricky. I think the main takeaway for folks is to get an intuitive feel again, I would use like the numbers 100 and 1,000 and 10,000 as your sort of touchstones. And then the other takeaway is that like a nested for loop is exponential, right? Because it's like one thing times another thing. And anything exponential grows really big. We'll look a little bit at like algorithms
nested-
that are logarithmic.
Yeah, a nested for loop is not quite exponential.
Oh, I apologize. Yeah,
We'll
a good point.
we'll see that in a sec.
Yeah, I apologize. And I totally did just put my foot in my mouth, so I will pause.
No worries.
Yeah, thank you.
Any questions before we continue on? No. All right. So this is pretty much the summary of what these mean. So O of 1 is constant. It means the speed doesn't depend on the size of the input at all. Log n is logarithmic, and 10 times the data means two times more time. You can read the rest. So linear 10 times means 10 times, n log n 10 times means roughly 20. And then quadratic, so quadratic would be a for loop within a for loop. And that means it will take, if you have 10 times more data, that means you'll take 100 more times. Same here, exponential, factorial, it's exponential. And factorial is even worse than exponential, it goes a little faster. And it'll kind of make a little more sense with this graph here. We have log n and O of 1. These are pretty good. Like these are your best case. Excellent runtime. Then you have O of n, which is like, it's decent, not too bad. N log n, that's where it gets it's starting to get a little bad runtime wise. And then n squared is all the way up here. 2 to the n, this is exponential, it goes even faster, and then n factorial goes even faster. So we want to try to avoid these ones, but a lot of times, depending on what type of operations you want to do or what things you want to do with your data, you can't avoid them. So you just kind of try to you try to optimize as much as you can. Sometimes you cannot avoid them.
Isn't O log n worse than linear?
It is,
But
but no, sorry. I thought you said constant. It is not.
O n log n is what I meant.
N log n is worse than linear. So this is linear here. Yeah,
Oh,
n log n.
Yeah, I see where this, okay.
Yeah, n log n is just a little bit worse than linear. Actually, it's decently bad.
I didn't even see, I didn't see the O n down there.
This one, yeah.
I thought the middle line was linear.
Oh, I know it looks like it, but it's the scale of the graph is a little, yeah, just to show the exponential and stuff like that. I have a link to this website, which is where I got this from, but it has like common data structures and their operations, and it tells you like how fast each one is. So we see binary search tree. To be able to access search, insert and delete, it's all log n operations, which is great. So this is it's one of the faster data structures that you can use. So this is best case, or sorry, this is average case, this is worst case scenario. So this is, yeah, just wanted to show those. And then these are sorting algorithms, which you will probably hear of them. So we have quick sort, merge sort, stuff like that. Today you're implementing bubble sort, which in best case scenario, it's n, average, and worst case it's n squared.
Zainab, how do you decide if the cost of, let's look at the shell sort. If the cost of the shell sort is worth it, what's the benefit of shell sort over something else? Why is it ever used if it's so costly?
I've never used shelf sort. I think it has certain, I think it's very fast for small amounts of input, if I'm not mistaken. There's at the end of the slides, there's a YouTube video link that shows you sorting algorithms compared by speed. Like they give them the same input and you can see them all running at the same time and see which ones are faster. And that's pretty interesting. So yeah, with that, you kind of just try to make your best judgment and pick the best one. Sorting algorithms, they exist, but doesn't mean that they're all like, there's like we have, what was it? Where is it? Here, bubble sort. Like selection sort is pretty bad all across the table. But it's still an algorithm that exists that someone wrote. Doesn't mean that you're probably going to choose to use it because it's slower. But yeah, so not all of the algorithms that exist should be realistically used in a program. They might have existed before the other ones existed. So that is why we know about them. Yeah, Kevin.
Are those Greek characters like the omegas and the thetas on those? Are those relevant to us at this stage?
I will get to that. Yeah, I'll
Okay.
show it to you guys. Okay, so we saw like what goes inside the parentheses here. So these are the typical ones that you usually see, but they can take any form. You don't have to worry about this. This is only when people are trying to like really get into the heart of it, and they're trying to compute different things. But yeah, it can take many forms. But for our cases, these are the ones that you're usually going to reference. And so there are some variations in the industry, or when people are interviewing. When they say big O, they usually mean like, what's the worst case runtime, or some of them actually mean what is the average case. So you just define whatever you want to define and then answer based on that. So you can say like, oh, okay, big O, I'm gonna say worst case scenario for this algorithm is this. So yeah, this is just what these all mean. So big O is, what is it called? It describes upper bound, so worst case scenario. Omega is the lower bound, best case scenario. Theta is exact bound, so it usually takes like big O minus omega. And then little o is the upper bound excluding the exact bound. So you don't have to worry about these, but I just wanted to share them in case you ever come across them. So there are different ones. This is kind of how they look. Yeah, so big O, big theta, or sorry, big omega, and then theta. Little o, I think this is little omega, if I'm not mistaken. Yeah, it is. But yeah, just kind of wanted to show them here. Any
That is
questions?
cool. I have not seen the other omegas in a minute. That's all I
Yeah.
wanted to say.
Yeah, I only saw them in my algorithms class, so. Yeah. Okay. So here is an example of a constant runtime. So we're just taking the first two values in an array and then printing them out. So this one doesn't depend on the actual array size, even though we are accessing the array because we're only grabbing the first two elements. So this is just an example of O of 1. If you had like a bunch of other operations that still don't rely on the size of the array, it's still O of 1. Okay, so an example of log n, so this was another good quick algorithm, is binary search. So this is generally how binary search works. You have an array and you identify the left side of the array, you identify the right side of the array. So this is the indices, right? And then you check while so while the indices are still on the left and right side, find a middle. So the middle is going to be left plus right divided by 2. So you're finding the middle point, and then you're seeing, okay, is my value less than the middle point or greater than? If it's less than, then I want to only check in the left side of this partition of the array. If it's the right side, then I want to do this. And then you keep looping through until you get to your correct answer. And this is what binary search looks like. So it'll restart in a sec. So here it was looking for 37. So here it starts in the middle. We know 37 is still larger. We go to that middle, larger, and then smaller, and then yeah. So here it only takes 3 steps versus a sequential, like looping through every single element. It took, I think, 11 steps. And this is the worst case scenario of a binary search, where every single time it like goes to the middle, it doesn't find it yet until it gets to the last possible one. So worst case scenario is just 4 steps versus worst case scenario here could be 16 for sequential. And this is where log is powerful. So if you kind of drew a tree, so even if this was a binary tree, this is what a binary search tree looks like, right? It's ordered. And so you get to this point, at most you are taking 1 path down. So here, here, here. So that is 4 nodes that you're touching. That is why it's considered fast. Any questions on this? Kenneth.
Zainab, so without getting too far into the CS side of else, I'm going to try to ask this to try, but how exactly will knowing big O notation for our code, will that help us with our knowledge base that we have now, assuming that we were all on the same level? How will that, knowing it beforehand, how will that affect the code that we write, and why is it beneficial to know big O?
It'll hopefully give you a tool to evaluate the code that you write and see how slow could this be if I was doing this on a big scale. So it is pretty helpful. I think it'll make a little more sense with the other examples. Yeah, how about we get back to that in a few? Yeah, okay, cool.
And I'll just throw in too, it helps with the code that you don't write and the things you avoid doing. Because you're just kind of like aware that, hey, if I write, like the nested for loop is the simplest example. If I have a really big amount of data and I'm using a nested for loop, that's going to take a long time. And so let me find another way.
That's what that's the example that I was going to get to.
Oh,
we'll
sorry.
See it in the slides. So no, it's okay. It'll make sense in the slides. So, okay, an example of O of n, so this is linear, is just a regular for loop. So we're looping through an array and we're doing some operations inside. So these are, again, negligible, but the actual loop means that we're at least doing enough operations that are the size of the array. So here, what are the time and space complexities for these two? For this, I mean, this entire algorithm. So here we're looping through an array and doing some stuff, and then afterwards we're looping through the array and then doing some other stuff. Okay, so I'm seeing an O2 of n Does anyone disagree?
Wouldn't it be n squared?
Why would it be n squared?
Because you're looping through the array twice. So the first for loop you get n times through that number, through that array.
Mhm.
But then the second time you get another n. So it's O of n
Mhm.
combined. So
So the difference is when they're not, so we see here there's one loop and this is O of n, and then afterwards there's another loop that's O of n on its own. So those are going to be added together. So we saw in our first example that we added up all the different ones. So here, time would be O of n. Space is constant because we're not actually creating like a different another array based on this array. We're just creating variables, and that is constant. Does that make sense? Yeah. Awesome. Okay, so before we get to quadratic, which we saw from our chart earlier, so n log n is still before quadratic. N log n, some people call it quasi-linear. I don't hear that often. You just say n log n. So there's not a lot of algorithms that are n log n. I will show a sorting algorithm afterwards that is this, but this is an example of this. So you have a for loop, you're looping through the array, and then for each iteration of that loop, you're doing a binary search. So because this is nested inside of this, you will multiply. So whenever you have, if it's like there's one loop separate than another loop, you're adding, but if it's an operation within a loop, then you multiply them together. So for this one, this would be O of n times log n, so it's n log n. Questions on this? Okay. So what are the time and space complexities for this one? It's not log linear. I forgot to crop it out. I edited it because you see here we were doing a binary search. So here we're doing a binary search first. We're trying to search for number 5 in this array, and then we are looping through the array. So what is our final? So
log n, was it log n plus on? I mean, would log n even matter at that point?
No.
Like undominant term? So it's just O. Okay.
Yeah. So O of n, and then what about space? So time complexity is O of n. We got a 2n. So that means it would be an n. Okay. Let's see. There we go. Oh, I cropped it out from here, but for here, not there. But yes. So the time is O of n, and then space is O of n. Can someone tell me why the space complexity is O of n?
You got to traverse the list, right? The array.
So the array already existed. Us traversing it won't add extra space in the runtime. What are we doing here specifically that adds? Yeah,
Appending.
Exactly. So we're creating an array the same size as the input. So that will take up more space. Okay, so another example of n log n is merge sort. So merge sort, what it does is actually, I think this link is better at showing it here. So you pretty much divide you divide your entire array into smaller and smaller sections, and then you merge them while sorting them. So you get to like two per section, and then you look at them each individually and you say, okay, 7 is greater than 14, so now I'm going to order them this way. 3 and 12, 9 and 11, 2 and 6, and then you merge them all the same way. So effectively, it's like a binary search in the way that you're only like you're sectioning off like half of the array, but because you touch all of the elements every time, this is going to be n log n. It's a little confusing. We can look into it a little later if you have more questions. But this is also the code of it, if you're interested in looking at it later. Okay, let's continue with this. Okay, so n squared, so a quadratic runtime. Quadratic will happen whenever we have a nested for loop. So a for loop within a for loop that will give us quadratic runtime. What about the space complexity of this one? What do you guys think? So if we have,
Is it n?
why would it be n?
You're creating one array also, or less?
Okay, what size is this array? So we are creating one array, but we're going for each number in the array, and then for each number in that array again, and then we're appending here. So this will actually be O of n squared for both space and time, because let's say you have 4 numbers in your array. So you're looping four times in the first loop, and then for each loop you loop in the first loop, you're looping 4 times again. So that's 4 times 4. And if you're appending for every single time, for every single piece of that loop, that means you end up with n squared. So you end up with 16 elements in this array versus just 4.
Makes sense.
Yeah, awesome. Zach, you're asking if you should be afraid of n squared. You should be wary. Yes, you should try not to have nested for loops if you have big input. It's not too horrible when you have smaller inputs. But yeah, so be wary of nested for loops if you can avoid them. So back to your question, Kenneth, like what will we be using this for? If you see that you have any of these patterns, like if you have nested for loops, if you have 3 for loops that are nested inside of each other, that will cause performance issues later on if you have a bigger input. So pretty much a takeaway of today is if you see that you're doing like the worst time complexity ones, maybe you want to refactor your code. Try to figure out a way of doing the same thing that you want to do, but in a quicker way, pretty much.
Totally. And I just want to add on to that, saying that exactly what you're saying about refactoring. I threw it in the chat. Like, if you get it working with a nested for loop, that's awesome. Then when you get it working, go back and refactor it and look at how to make it more efficient. And this is where that saying first make it work, then make it right, then make it fast kind of comes from. Because if you have to choose between getting stuck or using a nested for loop, unless your input size is like tens of thousands, go for the nested for loop and then revise it later.
Is there trouble? Are nested for loops bad, or is it nested for loops that use arrays bad?
Nested for loops that use the input is bad. So the array is the input, and we're kind of trying to see based on the size of this input, how bad is this algorithm? So if we had a nested for loop and this is running like a few times and this is running a few times, that's still technically constant because you're not looping through an array of an arbitrary size. Because a lot of times when we're processing data, like your application needs to process a list of apartment listings, let's say. You don't know how many apartment listings are in your database. You just need to be able to handle them. So if you have a relatively small amount of listings because your app is new or your company is new, then this would not cause you issues. But the more people that use it, the more data you have, then you'll start seeing your program slow down, and then you have to go back and figure out why and refactor, and it's a whole thing. Yeah, Nick.
So I mean, any way that you kind of program something, you're going to need to go through the same amount of data, correct? So like I'm not understanding if not using a nested for loop as opposed to maybe breaking it into two different functions or just finding some other way to do it, you're still going to be traversing the same amount of data. So where is that speed, I guess, being saved?
So having two separate for loops are different than having a nested for loop. So if you have two separate for loops and each array, and the array is like size 4, that's only, you're doing that 8 times versus a nested for loop is 16. Scale it up to an array of 10. Oh, sorry.
I was going to say 2 for loops, one after the other, not nested, is like 10 plus 10 equals 20. One for loop inside another is, and I'm probably going to get this wrong because you were saying it's a quadratic, not exponential. One for loop inside another is
100.
100. Yeah, thank you. I needed help with my brain there. Yeah, it's the difference between like addition and multiplication.
So not just in relation to for loops, but in like, say there's for loops weren't part of it, but just solving this in a different way. I'm just trying to grasp where this speed is saved in another way of solving it. That's what I'm trying to, I guess, kind of see.
It's the most or the main way that you're saving time is with the largest amount, or with the algorithm that is taking the largest amount of resources or largest amount of time. So maybe making like little tweaks to, so there's always ways to improve your runtime. If we were like I don't actually know how Python does this in the background, but like in C or something like that, just changing where you are defining your variables will cause like speeding or will cause your runtime to improve, but on a very, very small scale. So there are little tiny things that you can do which might be negligible in time saving if you are not really processing a lot of information. But when you are processing a lot of information, having a nested, like having 3 nested for loops versus 2 will make a big difference. And then having just 1 for loop, so that's why like with time complexity, you kind of want to tackle the hardest hitting one first, and then you can do smaller optimizations. Yeah, Luigi.
Yes. Would the time complexity still be the same if if we just happen to like take the for loop and put it into a new method by itself, and then add that for method into that for loop right here?
No, it would be the same.
It would be the same.
So yeah, so if you took this out into a function, whatever you call it, and then you call that function from in here, it would be the same thing, because you're still, for every iteration in this loop, you are looping through again. So it doesn't matter if it's right under it or if it's called by another function, it's still doing the same operations.
Gotcha.
Any other questions?
I don't know if it would be helpful, Zainab, because it's not exactly what we're looking at now with quadratic, with n squared. But with the question about like how do we save time and effort, that cool visual we just saw of like the binary search for the other search, I thought was a really good example of that in like another context.
Yeah, that's true. Like here, having an O of n versus an O of log n. Log n is so much faster than O of n.
Yeah, this is like, it's not a nested for loop, but I think it's like a for loop that just goes through the whole thing versus an algorithm that takes a clever approach.
Yeah,
Yeah,
that's a great,
and
that's a great example.
yeah, we don't have a good slide to show like a nested for loop for something else, but that's a good example of like, again, there are like other approaches instead of nested for loops that we could take that will be more efficient in that same way.
Definitely.
Yeah, and thank you for jumping over.
Of course, thank you. Okay, for this one, what's the time complexity?
System that I have most of the familiarity with is but I've only ever engaged with Chinese.
We have hot
Yeah,
mic
mic
somewhere.
Yeah, let me see if I can.
Is it quadratic? And wait, n cube, my bad.
N cubed, yeah. So this time complexity is n cubed. What about space complexity?
The same.
Darius, yeah. Yeah, Luigi. Exactly. So both of them are going to be n cubed. For this
Can
one.
you go back and talk? Maybe I missed a slide, didn't understand the slide you back. I understand the time complexity, but I'm not getting the space complexity.
So the space complexity is how much extra memory are you consuming while your program is running?
That's part of what interests me so much. Like,
so here we have, we're creating a new array while this program is running here. And this is going to run n times. And then this is going to run n times as well. So that's n squared already. And then this is going to run a third one, n cubed. And so for n cubed times, we are appending a new list item. So that list will grow n cubed based on the array size, because we're creating a new array that is, so if the size of the array was 2, it would be 2 to the 3. Does it? So that the size of the new array, huh?
I get that. That's cool. I got it.
Okay, awesome.
So Zach put a good question in chat. If you were to say our append number, would that be ON space?
No. So the appending itself, since it's within the last for loop, that means because it's running n cubed times, this specific line is running n cubed times, it will take up, or it'll append that many items onto the list. If I had this one layer up, so if I had this append on this level, it would only be n squared.
Okay,
because
that makes sense.
Yeah, because it's not actually running a third time and adding on like another n elements onto it. Any more questions?
So
yes, so
go ahead.
So basically space is the difference between the output and the input.
I'm sorry, space, yeah. So space is not necessarily the output itself, but how much memory you're using while the program is running. And one way of kind of demonstrating this is what you're saving into like a new array that you're creating, or if you're creating a dictionary based off of the data that you're pulling in, then that is also going to be affected by the size of the array. Did that answer your question?
Yes, it did.
Yeah,
Thank you.
okay.
So I was gonna kind of ask, so in a lot of cases, like just making new arrays instead of having, you know, a loop inside of a loop that you can kind of just manipulate different arrays would make your time better, but that would affect your space, correct? So
yeah,
I'm assuming there's just an optimal, like, hey, with this problem, you kind of want to try to do time space together versus just like, I mean, I guess it just depends on the situation, right?
yeah. You want to try to optimize both, but you might need to take a hit somewhere versus in another place. So you might need to take a hit a little bit on the space versus the time if you have extra space that you can afford to use, versus the time, maybe the system. So an example where you wouldn't really care about time as much is if you have like some job that is running overnight to sync up data between two databases. So no users are affected as long as the data gets copied over correctly and whatever needs to happen happens. If this takes 20 minutes or if it takes 3 hours, it kind of doesn't matter at that point. If you don't care about the time, then that's fine. But if you're making an application that is effectively or directly affecting users, then you would probably want to make something fast, because you know the struggle of, like, if you're on a website and it's taking way too long to load, you're just like, okay, I don't want to be on this website anymore. So yeah, that's sometimes you have to take a hit somewhere. Darius, did you have your hand up, or?
I did. My question was going to be, if you started deleting the data, that wouldn't affect the space, would it?
No, if you're deleting the data from the array and stuff, no, it wouldn't. Yeah. I mean, there might be some weird, like if you're deleting from the array while it's running, it'll like run less maybe, and the time complexity would go down. I don't know. That's a very special case, but yeah, the space wouldn't be affected if you're just doing anything other than creating new things in memory that take up as much space as the original thing, or even more. Okay. So exponential, so 2 to the n. An example of this is our Fibonacci recursive function. So if we say that we want to do a Fibonacci of 5, you guys have all seen this function, right? Fibonacci function. Okay. Okay, so if we said we want fib of 5, then what it would create under it is, because it's returning fib of 4 plus fib of 3. And then for each one of these, you have another tree that opens up, and it ends up being 2 to the n minus 1. That's the actual complexity of it, but because we don't care about constants, it's going to be O of 2 to the n. So this one is, if you're trying to calculate the Fibonacci sequence for very large numbers, it gets very big very quickly. It's not optimal. And the way to actually make this faster is to do, I think, like the sequential way of running the Fibonacci sequence, which I'll share with you guys later.
So the complexity of this one is because it's using recursion.
Yes, yes.
So recursion is bad. Got it.
No, no, not always. So, so you can refactor. I'll show it to you guys when I'm doing the demo, actually. But yeah, we'll get to the refactoring of Fibonacci. I just want to show
Yeah.
our last one before we go to break.
And-
Mhm.
And I know you were kidding, Icarus, but to put on the teaching hat, what's bad is not having a rough understanding of the complexity of the algorithm you are using. Like there are good use cases for nested for loops, for recursion, but we just need to know what we're looking at when we do it.
100%.
If Fibonacci is only addition, I don't get why it was N2.
So it's adding, but it's 2 to the n actually. So for each one function, it's splitting out 2 functions. And it's going to do that for the 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we ended up with 15. What's 2 to the 4?
Question,
That's a
that's not the full tree, isn't it? It's supposed to be like a diamond shape.
No, this is it. This is the full tree. So we
'Cause
started
you have
out.
to reassemble too. You have to reassemble. It's not reassembling in here.
Oh, but to reassemble, it's returning back. So this returns something, this returns something. And so from that return, it's going to return the addition of this and this. So fib1, fib0 will return, fib1 is going to return 0. Fib0 is not going to return anything.
Yeah, the tree is really
Yeah.
only showing like the function calls that's happening. And Luigi, you're right that like we sort of just implicitly have to trace the return statements back up the tree. We're not like mapping that part up.
But that's not geometric expansion, or I don't see how it's geometric expansion. It's kind of like partially geometric.
What is geometric expansion? I'm actually not.
1, 3, 9, 27, or 1, 2, 4, 8, 16. Because it's only populating on the left side of the so in the first iteration, there's 2 things. 1 becomes 2, and then 2 becomes 4, and then 2 does not become 8, but it becomes at 7 or 6. 2 becomes 6. So anyway, I don't think it's going to make a lot of difference. Just I didn't understand how. Still don't fully understand why Fibonacci is 2 to the n.
It's not Fibonacci, it's the recursion that's giving it to the end. Because it calls the function every single time that feeds back into it.
Yeah. The Fibonacci sequence is actually 2 to the n minus 1. We'll talk a little bit more about that later. Any more questions actually before?
What is the space complexity for that one?
The space, I would say, and this is it's not, we're not saving anything in memory, but we are making new function calls. I'm actually not sure. I will look that up.
Yeah, I'm not sure either.
Back to you.
It's also like it's not quite arbitrary what we count, but like like not every, like if you add 2 things together, we're not counting that as an operation when we look at time and space complexity. So I don't know if we care about the space complexity of the call stack or not. That is a good question. We don't have some variable in memory that is growing. Yeah, I'm with you, Zainab. Gotta look it up.
Doesn't the call stack grow? I mean, that's what's maintained in memory.
Yeah. The call
And you
stack
can
is
actually
growing.
hit a recursion cap in memory if you're going too far or too deep.
Yes, for sure. That is to protect from infinite recursion loops, and it could if it gets too far, it could corrupt your memory and something bad, but Python and stuff already stop
Oh.
it. But yeah, from what I'm seeing, some of the people are saying O of n. But yeah, we'll get back to that. I am not sure. Okay, so
Yeah, well,
and
that's a good question. We'll follow up about the space complexity question.
O of n factorial. This n factorial, you guys should know because there was an example or an exercise of this, but to find a factorial of a number, it's that number times the number minus 1. So 4 factorial equals 4 times 3 times 2 times 1. So this would end up being factorial for yeah, we'll see everything running in a bit. So I made this little program that tested different sizes of n and kind of saw the runtime of those. So O of 1, they all kind of took like a second. Log n, they all took roughly a second. Some of them were even faster than the ones after or the ones before, which was weird because when you're trying to calculate like small time, like the hardware will affect it. There's a lot of little things that will affect it when it's like in portions of a second. So O of n here, it was growing a little bit, like growing steadily. N log n, it started off pretty good, and then when we got to, what is this, 1 million and 5 million, then it started increasing. N squared, I had to cap it at 10,000 because it was already taking over 8 seconds. 2 to the n, I had to cap it at 40 because it was taking 27 seconds and I didn't want to wait too long. And then n factorial, just stopping at 9, it was already 98 seconds. So this was just, yeah, something to show you guys. We went over a little bit. Let's take a break.